It's time to finish up section 3.6, polynomial and rational inequalities. Our first example will be a poly, and then after that we'll do a rational. And let's see what we got going on here. Solve and graph the solution set on the real number line. Ooh, now this is a little more complicated than the ones we saw in class yesterday. But the song and dance is the same. We're going to get everything on the left side and set it less than or equal to 0. So on the left, I already have my x to the third and my x squared. I will subtract my 4x and subtract 4 from each side. And now we are less than or equal to 0. All right, what we did yesterday was factor, and this is a 4-termer, and it's the highest power is x cubed. And that should be a clue to maybe check factor by grouping. So here I'm going to group it off, and if I pull out of the first group an x squared, I'll be left with x plus 1. And if I factor, remember here we got to pull a negative out, so I'm going to pull out a negative and a 4. And this was a minus 4x. When I pull out the negative 4, x is left in its place. I'm going to factor a negative 4 out of a negative 4, so that'll change the sign to a plus, and it'll be a 1, less than or equal to 0. All right, now we do have two binomials. The first one is the repeater. Here is an x plus 1, so that is one of our two terms. And the other is made up of the leftovers, x squared minus 4. And we can either set this equal to 0 here, or maybe some of you like to factor a difference of squares into a sum and a difference. So we can factor the x squared minus 4 down to an x plus 2, x minus 2, and then we still have our x plus 1, and that is less than or equal to 0. So we have our polynomial fully factored, and we set each factor to 0 to find our boundary points. So I will abbreviate BP, boundary points. If I set my first factor equal to 0, I would subtract 2 from each side and get x is negative 2. And then here I would add 2 to each side and get x is positive 2. And then here again I would set it equal to 0, or less than or equal to 0, and subtract 1 from each side and get negative 1. So we do have some boundary points. I do see a little bit of a problem. Two of them are consecutive, a negative 1 and a negative 2. So we will have to evaluate a fraction to see what happens to our function in there. But let's put our boundary points down. We got a negative 2 and a negative 1 and a positive 2. And let's see here. I guess we can hop over to this next slide where we have our interval stuff set up. And let me go back here. And I might as well bring along our graph to that next slide also. Okay, our boundary points have chopped up our intervals. We're going to go from negative infinity to negative 2. And then from negative 2 to negative 1, that'll be the tricky one. And then from negative 1 to 2, and then from 2 to infinity. All right, we have 4 intervals to check out this time. We have one more because this is one higher power. It's x to the third. Yet the stuff we did yesterday was x squared. And again, here's our polynomial we're going to put them in. And sometimes I might even do this. It's remember, when we're doing this evaluation, the thing we're really concerned about is not the number that comes out, but just its sign. Is it positive or negative? So I'm going to copy my factored form and paste it over here. And I'm going to shrink it up just a little bit and put it up top. All right. Now watch, this is pretty slick here. Negative 2 to negative infinity. I like using, nice whole round numbers. Negative 10 works. And here we have 3 factors that are multiplied together. Again, we're not worried about the number, just the sign. And if I plug a negative 10 into the first factor, negative 10 plus 2 is negative. Negative 10 minus 2 is negative. And negative 10 plus 1 is negative. If I multiply 3 negatives, I get a negative. Is a negative number less than or equal to 0? Yes, that is true. So we will color in that part of the graph. Okay. Between negative 2 and negative 1, well, the only thing that works in there, I guess, would be negative 1.5 or negative 1.5. Let's write it as a decimal. All right. And again, we have 3 terms. We're only concerned about the signs. Negative 1.5 plus 2 is positive. Negative 1.5 minus 2 is negative. And negative 1.5 plus 1 is negative. Positive times negative is positive. Is a positive number less than 0? No, that's false. Okay, between negative 1 and 2, great number hidden in there is 0. If I plug 0 in to each of those factors above, 0 plus 2 is positive, 0 minus 2 is negative, and 0 plus 1 is positive. Two positives multiply to a positive times a negative is negative. Are negative numbers less than 0? Yes, that is true. All right, last one. Ooh, why did I put 8? That's supposed to, ooh, I can do this. Why not? That's not an 8, that's an infinity. From 2 to infinity. All right, let's plug in, I guess, a 10 works. Nice number. 10 plus 2 is positive. 10 minus 2 is positive, and 10 plus 1 is positive. All positives will multiply to a positive. Is a positive number less than or equal to 0? Absolutely not. That is false. So let's color in our graph. Ooh, and notice too, this is less than or equal to, so we will use brackets. From negative 2 to the left, that was true. So we're going to color that in. And then our next true one was from negative 1 to 2. So I will also color in from negative 1 to 2. And then the rest of it was false. All right, let's do a little, this is a one-dimensional representation of that polynomial. It's a slick little check to think about this as two-dimensional. Okay, the original polynomial was a positive x to the third. Think about end behavior. Positive cubics go up to the right and down to the left. And each of these were first power, so we know at each we will cross the x-axis. And we were looking for less than 0. So I'm down here under the x-axis, so that's why we colored in from negative 2 to negative infinity. And then I go above the axis, so we're positive, so we are false there. We didn't color in that part. And then we go back down underneath, and now we're under the x-axis again, and that's why we colored in the interval from negative 1 to 2. And then we cross at 2, and our end behavior is up, up, and away to infinity and beyond. So that does sort of verify or check that we had our conclusions were correct. Again, we wanted less than 0. Where is this graph underneath the x-axis? From negative 2 to negative infinity, and between negative 1 and positive 2. Alrighty, that was pretty fun. Let's see what's going on next. Time for rational inequalities. Remember, rational inequalities just look like fractions. There's numerators and denominators. A rational inequality is any inequality that can be put into these forms. F of x is our inequality, or f of x is our function, and then we have less than 0 or greater than 0, less than or equal to, greater than or equal to. And of course, f of x, f, is a rational function, and an example would be something like this. 3x plus 3 up top, 2x plus 4 in the denominator. The inequality is in the form of f of x greater than 0, where f is our rational function, 3x plus 3 over 2x plus 4. The graph, I did forget to cut and paste that into the slideshow here. You can open your book and look at it as we go through. We can find the x-intercept of a rational function by setting the numerator to 0. So we set that 3x plus 3 equal to 0, and we do a little algebra and find x is negative 1. So that's our x-intercept. That will be one of our boundary points. Another boundary point would be any horizontal or vertical asymptotes. So where f is undefined, we find by setting the denominator equal to 0. If we set 2x plus 4 equal to 0 and solve, we get x is negative 2. That is another, it's not an x-intercept, but it is another chopping up of our domain, our x-axis, into intervals. So we have a negative 1 and a negative 2. So by setting both the numerator and denominator of the function equal to 0, we obtained negative 2 and negative 1. These numbers will chop up our x-axis into intervals. Negative infinity to negative 2, negative 2 to negative 1, 1 to infinity. On each interval of the graph of the function, or on each interval, the graph of that function is either above the x-axis, greater than 0, or below the x-axis, less than 0. If you examine the graph in the book carefully, you can see that it is above the x-axis from negative infinity until we hit negative 2, and then also from negative 1 to infinity, and it's shown in blue. So thus the solution of the inequality greater than 0 is negative infinity to 2 union with the set from negative 1 to infinity. By contrast, the graph of the f lies below the x-axis for all x's between negative 2 and negative 1. In the book, that's shown in red on the graph. So thus the solution set of this less than 0 is negative 2 to negative 1. So the first step in solving a rational inequality is to bring all terms to one side, getting 0 on the other side. then express the rational function on the non-zero side as a single quotient. You got to get it down to a single fraction. The second step is to set the numerator and denominator of that function equal to 0. The solution of these equations are our boundary points that will separate our real number line into intervals. From this point on, it's exactly the same as the procedure we have used for polynomial inequalities. So let's try one out. Solve and graph the solution set of x plus 1 divided by x plus 3 are greater than or equal to 2. So let me move this up here. Step 1, get everything on one side, 0 on the other. So I'm going to have an x plus 1 over x plus 3, and I'm going to minus 2 from both sides. Now notice I'm going to sort of write it up here, minus 2, and now it is the whole thing greater than or equal to 0. Now notice too I left a little gap in here because this right now is a 2 over 1. We want to add these and get it as a single fraction. So what would my common denominator be? Well, this is x plus 3. The denominator here is 1. So I want my denominator to be x plus 3. If I multiply this denominator 1 by x plus 3, I got to do the same thing to the numerator. Oop, that's a terrible 3. That's a little better. Okay, now we are ready to make this a single fraction. Denominator is already common now. It is x plus 3. What's our numerator going to be? Well, this numerator piece is x plus 1. That comes down as is. Here we're going to have to distribute, and don't forget this minus sign goes with the 2. So negative 2 times x is minus 2x. Negative 2 times 3 is minus 6. And this is greater than or equal to 0. All right, let's simplify this down a little bit. We want it to be one nice, neat, rational expression. Our denominator is not going anywhere. It's going to stay x plus 3. What are we left with in the numerator? 1x minus 2x is negative x. 1 minus 6 is negative 5. Greater than, equal to 0. All right, let's find those boundary points. If we set the numerator equal to 0, negative x minus 5 is greater than or equal to 0. Let's see, we can add 5 to both sides. Why greater than? Remember, equal to 0, equal to 0. Okay, let's add 5 to each side. Negative x equals 5. So divide by a negative, and x is negative 5. Let's see the denominator. Set the denominator x plus 3 equal to 0. Subtract 3 from both sides. X is negative 3. So we have two boundary points, negative 3, negative 5. There we go. I clipped a little bit of my denominator. Okay. So those are our boundary points. And let's see. Yeah, we'll take that over here to the next slide. Yeah, and I can take this with me. And 3 and negative 5. Oop. And I'm going to take this with me. Oop, get that out of there. I'm going to take this along for the ride also. Copy that. Paste it over here. All right. Boundary points, negative 5, negative 3. So here's negative 5, here's negative 3. Nice to see that visually, to think about our intervals. So of course, negative infinity to negative 5 is where we begin. Then we pick up at negative 5 and go to negative 3. And then the last one will go from negative 3 off to infinity. Test values, negative 5 to negative infinity. I like negative 10, nice number to work with. From negative 3 to negative 5, of course, we'll have to work with negative 4. And then 3 to infinity, 0 is nice. Okay, let's see if our inequality is true and false. Now here we have a fraction. So let's see what our sign is going to be. Plug negative 10 in the numerator. Negative 10 is positive 10. 10 minus 5 is positive. In the denominator, negative 10 plus 3 is negative. A positive divided by a negative is a negative. Is a negative number greater than 0? No, that's false. All right, let's try the next interval. We're going to plug a negative 4 in. Negative 4 is positive 4. 4 minus 5 is a negative numerator. And our denominator will be negative 4 plus 3, which is also a negative number. Negative divided by negative is positive, and positive is greater than 0. So that interval is true. We will color it in on the graph. And then last but not least, 0. If the x is gone, we're left with a negative 5 in the numerator and a 3 in the denominator. Negative divided by positive is negative, which is not greater than 0. So that is also false. Okay, let's see what we got then, and it is greater than or equal to 0, so we will use brackets. And we will color in between. So what the graph probably looks like here is at negative 3, we have an asymptote, negative 1, 2, 3. We will have an asymptote. And then at negative 5, we have an X-intercept. So go 2 more, and then that is an X-intercept. And we know that it is greater than 0 or above the x-axis only on that little interval from negative 3 to negative 5. So it looks like we're heading up as we approach the asymptote, and over here we're under. And for the other one, we're only above between negative 3 and negative 5. Yeah, so the other one will be under the x-axis the whole way and going down towards the asymptote. And there's our solution. When I see down in the corner a great question, let's see how great it is. Which boundary points must I always exclude from the solution set of a rational inequality? Ooh, I almost forgot this. Never include a value that causes a rational function's denominator to equal 0. Division by 0 is undefined. Now our inequality was, what was it, less than or greater than? It was greater than or equal to 0. Because of the or equal to, you think you're going to use brackets on both of those. But remember, what's going to zero out our denominator? That 3, negative 3, is going to zero out our denominator. So at negative 3, we don't want a bracket, even though our inequality has the or equal to. Dividing by 0 is always a no-no, so that will always be a parenthesis. Division by 0 is always a parenthesis, even if the inequality has the or equal to part there. So I guess that was a pretty great question. It caught me from making a silly little mistake. All righty. Couple for you to try. Pause the video, solve the inequalities, and then fire it back up and see if you got them right. All right. The first one is like the first example. Of course, get everything on the left. And that'll be a minus x minus 3. Ooh, that's a terrible 3. Is less than or equal to 0. 4 terms, highest is a cube. We are going to think about groups. Let's pull the grouping out. First one we'll pull out as an x squared, leaving an x plus 3. Here we will factor out a negative 1, and that will change that sign also to an x plus 3. If it didn't, the factor by grouping would not work. So we have 2 terms. Our first one is going to, one of them is going to be the x plus 3. The other is the leftovers, the x squared minus 1. And then I'll put my x plus 3, and that's less than or equal to 0. X squared minus 1, or x squared minus 1 is again factorable to a sum and a difference, and then we still have the x plus 3 term, and that's less than or equal to 0. So we have 3 boundary points. The numbers that will zero out each individual factors. A positive 1 here would zero it out. That's a boundary point. A negative 1 in the next solution would zero it out. There's another. And x plus 3 equals 0 means we'll have one at negative 3. So there are our 3 boundary points. All right, on the first one, from negative 3 to negative infinity, I would pick out a negative 10. So let's see what we got. Negative 10 minus 1 is negative. Negative 10 plus 1 is negative. Negative 10 plus 3 is negative. 3 negatives multiplied to a negative is a negative number less than 0. Yes, that's true. So we will color in that part of the graph. And it's less than or equal to, so we will use a bracket. Okay, next one, we're kind of constrained here. We only got negative 2 to work with in that interval, at least as far as whole numbers go. Negative 2 minus 1 is negative. Negative 2 plus 1 is negative. negative 2 plus 3 is positive. So we get a negative times negative is positive, times another positive is positive. Is a positive number less than 0? No, that's false. So we're not going to color in that interval. Next test, 0. 0 minus 1 is negative. 0 plus 1 is positive. 0 plus 3 is positive. Two positives multiplied to a positive times negative is a negative. And yes, negative numbers are less than 0. So that is also part of our solution set. Okay, and then from 1 to infinity, let's choose 10,000. 10,000 minus 1 is definitely positive. 10,000 plus 1 is also positive. 10,000 plus 3 is also positive. Everything's positive. Is that less than 0? No. So we're not going to color in that part of the graph also. Now let's think about, again, this is a one-dimensional representation. We're trying to find where our graph would be under the x-axis. Again, think of end behavior. X to the third, positive cubic, is up to the right, down to the left. So that makes sense. We're down here under the x-axis as we come up and approach our first x-intercept. And then we're above the graph, so it's no longer true until we go back under, and now it's true again. And we cross at 1, our last boundary point, and then up to infinity and beyond. So again, less than 0 means we are under the x-axis. In this little piece here, we were above the x-axis. We did not color in that interval. And then from here on out, we were above the x-axis, so we again did not color in that interval. Now be careful. Remember, don't fall into the trap of thinking that these always alternate. Here we had true and then false and then true and then false. If one of our factors had been of even multiplicity, we would touch but not cross the x-axis. So there we would come up and maybe bounce off and then come back down. So we could have 2 true or 2 false intervals right in a row. So be careful. Don't think it always is going to follow that pattern of true, false, true, false. Okay. What do we got for this last one here? That number line will work on this one also. Rational. So we got get everything on one side and condense it down to a single fraction. So on the left is 2x over x plus 1. And it's a positive 1 on the right. I'm going to subtract 1 on the left. And now it is greater than or equal to 0. Well, let's get our common denominator. Common denominator will be x plus 1. So I multiply my numerator 1 by the same x plus 1. And now I have a common denominator, x plus 1. So I can condense my numerator pieces. First the 2x. And let's do this all at once. Here I'm going to distribute a negative 1. Negative 1 times x is minus x. Negative 1 times 1 is minus 1. Greater than or equal to 0. See, what we're left with here now is 2x minus x, which is x, and then it's minus 1 over x plus 1, and that is greater than or equal to 0. Okay, boundary points. Set the numerator and denominator equal to 0. If I set the numerator to 0, I get a boundary point at 1. If I set the denominator to 0, boundary point at negative 1. Again, if you're thinking about a two-dimensional graph, the negative 1 is an asymptote, and the other one is just an x-intercept. All right, we do have some intervals to test out. Let's test negative 10. Here's my fraction. Negative 10 minus 1 is a negative numerator. Negative 10 plus 1 is a negative denominator. Two negatives divide to a positive. Is a positive greater than or equal to 0? Yes, that is true. So from negative 1 to negative infinity, we will color in that part of the graph. Oh, that's terrible. I can do better than that. Or actually, what I should do is just make this a little thicker. There we go. Okay, next interval has 0 right in the middle. That's a good one to test. If we test 0, get over there we go. Plug in a 0. 0 minus 1 is a negative numerator. 0 plus 1 is a positive denominator. Negative divided by positive is a negative number. Is a negative number greater than or equal to 0? No, that's false. So we will not color in the interval from negative 1 to 1. Last one, positive 10. Numerator, 10 minus 1 is a positive 9. 10 plus 1 is a positive 11. They divide to be a positive result. Are positive numbers greater than or equal to 0? Absolutely. So we are going to be going from 1 to infinity. Will also be colored in. Okay, now let's figure out brackets or parentheses. The inequality is greater than or equal to. So we will use brackets as long as we do not result in division by 0. -1 was our division by 0, or where that asymptote is, we do not want a bracket. So this will be a parenthesis. And then the other one that would zero out the numerator, the X-intercept, that one will be a bracket. All right. Looks good. Let's see what the homework looks like. Page 420, 35, 36, 37, 43, 44, 45, 57. Have fun.